A single electric arc strikes against a massive slab of structural steel inside a quiet, dimly lit shipyard facility. Heavy industrial welding demands perfection across seams that stretch for dozens of meters. Yet raw steel plates are never truly flat, clean, or perfectly aligned. When joining massive sections of a ship, even tiny gaps or surface twists create major structural flaws. Finding these errors after welding costs thousands of dollars and hundreds of wasted work hours. In simple factory assembly lines, like those making compact cars, industrial robots follow fixed path routines with ease. Metal parts in auto plants arrive uniform, clamped tight in identical rigid jigs. But heavy hull manufacturing operates under entirely different physical constraints. Giant steel plates curve, warp, and shift under their own immense weight. A robot following a rigid pre-programmed path quickly strays off course, laying down molten filler metal onto bare plate instead of the joint center. When standard automated equipment misses a seam, the failure creates a dangerous structural defect deep inside the metal. Manual torch operators used to watch every millimeter of the molten weld pool, making instant physical adjustments based on years of trade experience. Human eyes noticed when metal edges pulled apart or lifted under extreme arc heat. Yet human hands cannot maintain perfect speed and torch orientation across 100-foot hull plates for hours without fatigue. The industry needed machine precision guided by dynamic sight. The breakthrough came with real-time optical sensing mounted directly onto the robotic wrist tool. Positioned just inches ahead of the hot welding torch, a specialized laser sensor projects a thin, sharp sheet of light across the joint line. High-speed digital camera optics capture the line of light as it wraps over raw groove edges. This laser seam tracking head views the exact physical shape of the gap moments before the arc strikes the bare steel plate. That reflected light pattern carries precise mathematical geometric information about the seam. As the laser scans across the seam, integrated vision software calculates the exact depth, width, and center location of the joint in real space. If two steel plates taper apart or rise slightly out of alignment, the optical sensor detects the change instantly. The system maps the precise geometry of the metal surface hundreds of times every second without making direct physical contact. This continuous stream of surface measurements forms a dynamic real-time feedback loop for the robot controller. The sensor feeds raw spatial coordinates into the motion software driving the 6-axis robotic arm. Instead of following a rigid static code, the machine recalculates its spatial path while actively moving. If a plate dips down 3 millimeters, the robot lowers its torch by that exact distance, keeping the electric arc length perfectly consistent throughout the pass. Beyond simple spatial tracking, the control system adjusts critical process parameters on the fly. If the laser sensor detects a widening gap between steel plates, it signals the power supply to adjust electrical settings. The controller speeds up wire feed rates and increases electrical amperage to fill the extra volume. When the gap narrows back down, wire speed drops immediately, preventing excess filler metal from creating localized mechanical stress concentrations along the seam. This adaptive capability solves one of heavy industry's most stubborn physical problems: thermal deformation. When a high-energy welding torch melts steel at thousands of degrees, heat spreads rapidly through surrounding plate material. Steel expands as it heats up and shrinks as it cools down behind the moving arc. This uneven thermal footprint twists the unwelded joint ahead of the torch, shifting gap position continuously during active operation. Without real-time feedback, thermal deformation guarantees severe weld errors on long structural joint seams. As heat builds up along a ship hull section, the metal gap pinches tight or pulls apart mid-pass. A conventional robot continuing along its baseline trajectory quickly drifts out of the joint groove. Laser seam tracking neutralizes this thermal warp by monitoring the actual moving position of the seam rather than where the metal originally rested. Stepping back to the shipyard floor reveals the massive scale of this automated transformation. Massive gantry structures straddle steel plates measuring 50 feet wide across large bays. Multi-jointed robotic arms move along overhead tracks, laying deep structural welds into heavy double-bottom hull assemblies. Guided by laser vision, these giant machines maintain sub-millimeter positioning accuracy while traveling down long structural channels, continuously adjusting to real-world surface imperfections and metal warping in real time. This technology fundamentally changes the working environment for industrial metalworkers across the facility. Skilled tradespeople no longer spend grueling 8-hour shifts, crouched inside tight steel compartments, breathing smoke and holding heavy torches. Instead, qualified operators monitor multi-robot cells from climate-controlled booths. They inspect live sensor data profiles and fine-tune system variables, using high-level technical expertise rather than physical endurance to guarantee consistent weld quality. The structural consequences of seam welding errors in maritime shipping remain catastrophic if left unchecked. A missed joint section or internal void beneath a heavy weld bead can lead to fatigue cracks under relentless ocean wave stress. Ocean vessels experience massive bending forces at sea, where single structural weld defects can weaken an entire ocean-going ship hull. Removing weld defects at the source protects both valuable commercial cargo and human lives far out at sea. Traditional quality assurance relied heavily on slow post-weld inspection methods after fabrication finished. Quality inspectors used ultrasonic probes and industrial radiation tools to check completed welds for hidden internal cracks. When inspectors found defects buried deep inside thick steel joints, workers had to gouge out feet of solid metal using carbon arcs and weld the entire joint again. This grinding repair cycle added massive labor costs and severe schedule delays across shipyard projects. Laser tracking eliminates most post-weld repairs by catching geometry issues long before filler metal drops. By recording exact profile measurements during the process, the control system logs a permanent digital footprint of every millimeter of the seam. Engineers gain a complete, verifiable record of joint gap shape, heat input, and torch alignment for every structural weld. Quality control shifts from reactive repair work to proactive real-time process monitoring across production lines. Zooming in on the optical triangulation hardware shows the engineering rigor required for hot factory floors. Laser heads operate inches away from brilliant electric arcs, emitting harsh light, intense heat, and flying molten spatter. Protective air knives blow clear compressed air across optical lenses to sweep away smoke and airborne dust. Heavy optical glass filters block out bright blue arc light, letting only the specific laser wavelength reach the camera sensor inside. The electronic architecture driving these optical heads requires exceptionally high processing speeds. Industrial signal processors clear image frames, filter out visual background noise, and calculate joint center points in single-digit milliseconds. This processed spatial data travels over high-speed industrial network cables directly to the robot motion controller. The closed-loop communication happens so fast that the machine corrects torch position without slowing down its planned travel speed along heavy plate. Looking across global supply chains, the adoption of laser-guided welding redefines manufacturing efficiency. Specialized shipbuilders, heavy equipment makers, and pressure vessel fabricators complete complex steel assemblies in a fraction of traditional build times. Higher throughput allows yards to deliver commercial transport ships and ocean infrastructure faster, cutting backlogs and lowering capital expenditures across major industrial shipping networks and commercial marine fleets worldwide. In heavy structural steel fabrication for bridges and skyscrapers, the impact is equally dramatic. Unpredictable beam dimensions and mill tolerances previously limited the use of industrial robotics in structural shops. Laser tracking allows heavy gantry systems to weld custom bridge girders with varying web depths and angled flanges. The technology bridges the long-standing gap between flexible manual trade work and high-volume industrial automation across complex structural engineering projects. The integration of intelligent sensors also lowers the entry barrier for high-precision manufacturing processes. High-power laser welding and narrow-gap gas metal arc welding require extreme torch placement precision within fractions of a millimeter. Without automated seam tracking, setting up these specialized welding processes on large steel parts was financially unfeasible. Advanced optics make tight tolerance welding methods viable on huge, unmachined structural plates across diverse industrial sectors. This transformation alters the financial math of modern heavy manufacturing facilities. Facilities using real-time laser guidance report drastic drops in filler wire waste, shield gas consumption, and electrical power usage per completed joint. By preventing burn-throughs and incomplete fusion errors on expensive alloy plates, manufacturers avoid costly scrap metal and rework delays, improving operational margins across competitive global markets and demanding heavy production environments. Future advancements in sensor technology are driving even deeper machine intelligence into the welding head assembly. Emerging systems combine laser profile sensors with infrared thermal cameras and acoustic feedback units. These multi-sensor suites measure real-time cooling rates and internal arc stability alongside physical joint geometry. The robotic controller adjusts electrical power inputs to actively manage the metallurgical microstructure of cooling weld metal while moving smoothly along the seam. From tiny optical sensors to massive ocean-going ship hulls, laser seam tracking solves a fundamental physical barrier in modern industrial manufacturing. By giving industrial robots the sight needed to adapt to bending metal in extreme arc heat, technology turns unpredictable heavy handwork into a continuous, verifiable science. Steel structures built with real-time feedback loop precision are stronger, safer, and fully prepared to meet the expanding demands of modern global infrastructure.